This problem is on displacement velocity acceleration graphing. And just as a quick something to put on your note card, remember that if we have a displacement time graph and we want to go to a velocity time graph, in general we want to find the slope as we go to the right. And so as we go farther to acceleration time, we're going to take the slope again. If we ever have acceleration and we want to find velocity, we're going to have to find the area under curve. That general little chart should probably be on your note card somewhere to remind you that as we're going one way we do one thing, as we go back the other way we do the other. It also leads to the fact that whenever we have one thing graphed versus the other and we want to find something that is those two things multiplied and divided, we use the slope. If it's ever multiplied, we always use the area. So it leads to more generalized graphing things later on. In any case, we don't need to worry about that quite yet. We're going to start with letter A. Letter A is indicate every time t for which the card is at rest. At rest, since it's a velocity time graph, means that when the velocity is 0. So that's going to be here and here. So when the velocity equals, when time equals 4 or 18. So that's a typical part A, really easy, just read it off the graph, 4 seconds or 18 seconds. The next one says indicate every interval where the speed, remember, and then they give you a little clue, the magnitude of the velocity of the card is increasing. This is not the velocity, this is the speed, so that means we do the absolute value and we want it to be going up. So for this part, my speed is going down, but here, even though my velocity is going down, it's actually speed going up. So this section, my speed is going up. So that is from 4 to 9 seconds. And then the other way that my speed can go up is if it's positive and going up. So that's this section right here. So that would be 18 through 20 seconds. So this bit and that bit, right? Okay, now the part C says find the horizontal position. And so since this is a velocity time graph and I'm getting the displacement, I have to find the area for that. And so what I need to do is find the area up to whatever time I have. So it's up to 9 seconds. So I want to go up to this point right here. I need to find the area of this triangle. I need to find the area of this triangle. And remember, the area of this triangle down here has to be negative because it's below the axis, and this one's going to be positive because it's above the axis. And so I take those two displacements. And then there's a little tricky thing here because it says I have an initial position that I'm going to have to add once I'm done with all my areas. So that's kind of tricky, so make sure you're watching for that. Anyway, the formula for the area of a triangle is 1/2 base times height. So for this bit here, I take 1/2 the base, which is 4, times the height, which is 0.8. Then I have to add this base, which would be 9 minus 4, or 5, times this height, which is -1. That's what it takes the negative into account. That's where it comes from. And so when I do all this, I get -0.9 meters. But I have to add my initial 2, and so I get 1.1 meters. That initial 2, if you are in calculus, would be the plus c that you do when you're defining the integral. Just a quick math aside. Okay. Then I move on to for D, on the axis below, sketch the acceleration versus time. Now, acceleration versus time would be the slope of my line. So I have to go and find the slope of for all the different sections. So for this section here, I would take the rise, which is 1.8, or -1.8, so it's going to be a negative number. -1.8 divided by the run, which is 9, and I end up with 0.2 negative. So all the way for that slope, I have -0.2 for my acceleration. When I get to this next section here, I do the rise over the run. My rise on that one is 1 minus 0.4, which is 0.6, and my run is 3, and so I get positive 0.2 for that one. So that makes this whole section here positive 0.2. Then I have a little section here where my slope is 0. That's probably the easiest bit there. And this last bit, I have a much higher slope. It's positive, and my rise is 0.8 minus a -0.4, or 1.2 over 3, and so I get 0.4 positive, and the last bit is 0 right there again. And so that's what my graph looks like. It looks a little weird, disconnected, but that's because it changes really quickly from one to the other one. So remember, slope for acceleration, area under the curve for displacement. Now I have the last three problems on this, and for this one it says from t equals 25 until the car reaches the end of the track, the car continues at a constant horizontal velocity. So that's nice. The car leaves the end of the track and hits the floor, which is 0.4 meters below the cart. This is adding on the 2D kinematic at the end of it. So what I'm going to do is I'm going to set an x and a y column. And it turns out that I almost always find the time with y, and this actually is using that general equation, although I think I'm going to actually use numbers for this one. I'm going to use y first on this one, then I'm going to put x for the horizontal, because I know that this is horizontal and this is going to be vertical. It says it goes all in the x, so my v1 is 0 here. My a is negative 10. My displacement is negative 0.4. I'm looking for time. So I go d equals v1t plus 1/2 at squared. I get negative 0.4 equals 0 plus 1/2 times 10 times t squared. And so then I take, that's going to be 5. The negatives cancel like they always do. I get 0.4 divided by 5 equals t squared. And so t equals 0.28 seconds. So that's my answer for this one. And then I'm going to plug that into the x side. On the x side, from my graph, I can find that the v1 is 0.8. My acceleration is 0. My time is 0.28. I'm looking for displacement. I use the same equation, d equals v1t plus 1/2 at squared. My distance this time is what I'm solving for. Acceleration is 0, so all I have is 0.8 times 0.28, and I get that my distance equals 2.1, no, sorry, no, just so it was going place, 0.23 meters. This last bit is an energy thing thrown into this problem, and in this problem I have mgh going into 1/2 mv squared, so I set mgh equals 1/2 mv squared. They asked me to find the kinetic energy though, so this side is what I'm solving for. So I'm just, instead of putting that, I'm just going to put kinetic energy, and all I have to do is say kinetic energy equals the mass, which is 0.5, times g, which is 10, times the height, which is 0.4, and I get 2 joules. Pretty easy. And I'm done.